Hello and welcome to this video on what is a suppressor effect in statistics. My name is Geiser, I'm an instructor with QuantFish, and on this channel I present weekly statistics tutorials. I usually talk about multivariate statistical methods including structural equation modeling, path analysis, factor analysis, multi-level modeling and latent class analysis. If this is something that interests you, then please consider subscribing to this channel. Also, don't forget to check out the description for additional resources, including courses that I teach for QuantFish. In this video, I want to address the question of what is statistical suppression. What is a suppressor effect? And I want to do this from the perspective of regression analysis, even though this can also occur in other statistical analyses such as path analysis, multi-level modeling, structural equation modeling. But we're going to look at a very simple multiple linear regression example. And so for this purpose, I'm going to use the free software JASP, which allows you to run a variety of different types of statistical analyses, including regression analysis. You can download this program for free from the internet and it is very user-friendly. You can see in my data file that I'm using here, I have three variables that I simulated. So this is not actual data, but this is a simulated example to illustrate the concepts, but you might find something like that also in real data. My three variables that I generated here for this illustration are y, the dependent variable job success, and two predictor variables x1 and x2. x1 is verbal abilities and x2 is supposed to reflect the exam scores or final grade scores on some sort of relevant college exam or something like that. So let's take a look and let's see what suppression looks like or how it shows up in a regression analysis. You might have already guessed that I generated the data in a way that this will actually allow me to illustrate what suppression is like. So let's go to analyses here, and then I'm going to go to regression and then linear regression, and we're going to take a look at our dependent variable job success. So we're going to put this over here in the field dependent variable. It's the same principle as what you would do in SPSS, for example. And so then what I want to do next is I want to only consider the x1 verbal predictor first. So I'm going to put this here under covariates, and I'm not going to consider the exam scores for now. So I'm only going to look at a bivariate linear regression of job success on verbal abilities. And so you can see that on the right hand side we have the output, and under H1 we have the multiple R, the multiple correlation for a regression. In this case, it's equal to the absolute value of the bivariate correlation. That's 0.084. From the standardized regression coefficient in the last table, you can see that that is equal to the correlation in this case. So that's also positive 0.084. And so this means that there's a very weak, positive but very weak correlation between job success and verbal abilities. That is not statistically significant. The p-value here for the t statistic is 0.349, and so is the p-value for the f statistic, that in this case both are tests of the linear correlation, the Pearson correlation between those two variables, and so both of them return a non-significant p-value, and we see it's also in terms of the effect size, it's a very small correlation. So there's nothing there. So really verbal abilities in this example have nothing to do with job success whatsoever. It's not a relevant predictor. And that's at least what we might think at this point. We might say, okay, we can throw out verbal abilities from our regression model. This is not a useful predictor. This would be a mistake, however, as we will see now. So what happens now if we add our second predictor, the final exam or grade scores, into the covariates or predictors field here? Then you can see JASP updates the output, and now all of a sudden we have a multiple R, a multiple correlation of 0.861, which is very strong. This corresponds to a very strong R squared of 0.742, which means this model explains about 74% of the variance in the dependent variable. You can see adjusted R squared is similarly high. So it means there's a lot of variance in the dependent variable that is accounted for when we add this second predictor. And you might think now, first of all, okay, the exam scores are really relevant for job success. So this is really what predicts job success. Verbal abilities is a redundant predictor. We can kick that out of our model. However, when you look a little bit more closely at the coefficients table, so the regression slope coefficients in the last table, you can see that those regression coefficients that are given down below here, they are now, first of all, highly statistically significant. So when you go to the last column, to the p-values, you can see both the verbal predictor and the exam score predictor both have significant and very strong t-values. So the t-value here for the verbal predictor is -14. That's highly statistically significant. And the t-value for the exam score is positive and is almost 19, so it's also highly statistically significant. So now both predictors are or have significant partial regression coefficients. That's the first thing, and that might surprise you because we previously saw that the X1 verbal predictor by itself in a bivariate model did not have any predictive value. So the correlation was 0.08 and it was not statistically significant. And now all of a sudden that regression coefficient in the combined model with both predictors is highly statistically significant. And also when you look at the standardized regression coefficient, it is very strong in terms of its absolute size. It's -1.113. And also the standardized regression coefficient for X2, the exam score, is 1.473. So that might surprise you. And you might first of all think, oh, maybe this is an improper solution. Maybe this is a solution that is out of bounds. I have standardized regression coefficients that are smaller than -1 and one other one is greater than 1. Maybe that's an inadmissible solution. However, it is not. There's really nothing in the math behind a linear regression model that forces or requires partial regression coefficients to be between -1 and 1. They can be smaller than -1 and they can be greater than 1. And that is characteristic of a suppressor situation. That often happens when you have a suppressor variable in your regression model, that you find that standardized regression coefficients are abnormal in terms of their size and or their sign also. Notice this negative sign here. All of a sudden the verbal abilities predictor, even though previously mildly or very weakly positively correlated with job success, all of a sudden has a negative regression coefficient. So that's also strange, right? So that's also surprising because previously the bivariate correlation was positive. The other regression coefficient is above 1, and so that is something that we don't see very often in conventional linear regression analysis. However, it's perfectly admissible, it's perfectly fine, no reason necessarily to panic or reject this model. So this really shows us there's a suppressor situation. Now, before we dive more into the details of why this happens, I want to do one other thing, and I want to remove the verbal predictor from the model to show you what happens when we only look at the second predictor, the exam score. And so in that case, you can see that the multiple R drops. It's still strong, but it drops to 0.567. So that's the bivariate positive correlation, as you can see from the standardized regression weight, 0.567. That's the bivariate or zero order correlation between the exam score and the job success variable, and it's highly significant. So that's definitely a highly significant predictor. However, by itself, it does not have nearly the multiple R or the R or R squared that it has when we have the verbal predictor in the model as well. And you can see the standardized regression coefficient is also way different from the combined model where it was above 1. So you can see that there must be something about the verbal abilities as a second predictor that is useful in the model for R squared and multiple R, even though the zero order correlation between the verbal abilities predictor and the dependent variable is not substantial and is near zero and not significant. So yet this predictor has a role, a positive role in the prediction model, and that is due to its function as a suppressor variable. So what does this mean for x1, for the verbal predictor to be a suppressor variable? We can better understand this by looking at the bivariate correlations between all three variables. And that's something that we should always do. Whenever we run a regression or a path model or something, we should always be sure that we understand the bivariate associations between the variables, meaning we should look at scatter plots, we should look at the bivariate correlations to make sure that we understand what's going on at the zero order bivariate correlation level. So let's do that, and we can do this by going to correlation, and then we can select all three variables from our list. We put them over here, and then you can see that, as we saw previously, the correlation between job success and verbal abilities, the Pearson R or product moment correlation, is 0.084. Not statistically significant. The p-value is 0.349, same result as for the regression model. Also, the same result as what we've seen previously is that the correlation between job success and exam scores is substantial, 0.567, and it's statistically significant. So that's nothing new here, but what we have not seen yet is the correlation between the two predictors, x1 verbal and x2 exam. And you can see that bivariate correlation is 0.813, so very strong, a very strong correlation. Now, mind you, in a regression model with more than one predictor, the correlations among the predictors plays a role in the calculation, in the computation of the partial regression coefficients, the betas. So that model takes into account the correlation between the predictors. And so what happens here now is, at a substantive level, is that the verbal abilities predictor is highly relevant for exam scores. So in order to understand the exam, you have to have verbal abilities. However, in this example, it's not relevant for job success. So really what this role is of this predictor verbal abilities is that it suppresses variance in the exam predictor that is irrelevant for the prediction of job success. So we are taking out or suppressing irrelevant variance components in the exam predictor, and therefore increase the utility of the predictor x2. So the role of x1 is that it improves the predictive ability of the second predictor. It does not directly, it's not a direct, so to say, predictor of job success. It's not directly correlated with job success, but it is correlated with the second predictor and therefore is useful in the prediction, which is surprising, right? That's kind of surprising because we always learn in regression at the beginning multicollinearity or confounding correlation between the predictors, redundancy is a bad thing. Yet you can see that a high correlation between predictor variables is not necessarily a bad thing. It can actually help you predict the outcome or criterion variable better, because when a variable adds as a suppressor, it helps make other predictor variables better. It enhances the predictive ability or the utility, as we say, of other predictor variables. And that can be quite useful. If your goal is prediction, if your goal is to have a high R squared, make a good prediction of the outcome scores, for example, job success scores, then you may not care that this variable by itself isn't correlated with your dependent variable. If it helps you predict the dependent variable better, then you should by all means include it in your regression model, despite the fact that here we have multicollinearity. So that's an important message, so to say, that multicollinearity is not necessarily a bad thing. It could be bad, but it could also be helpful, like in the situation of suppression. So what we've seen here is called classical suppression or traditional suppression. In classical suppression, the suppressor variable is not or only very weakly correlated with the dependent variable. In this case, verbal abilities were not highly correlated with job success. But the suppressor variable in traditional or classical suppression is strongly correlated with the second predictor variable, which we saw here was the case, a correlation of 0.813 between the verbal ability scores and the exam scores. So therefore, this variable served as a suppressor variable that improved the predictive ability of the second predictor. Now, there are also other forms of suppression that I want to discuss with you. In addition to that, what I want to do next is I want to look a little bit more technically, more formally into how suppression is defined mathematically, or how it can be defined, and I want to discuss those different forms of suppression that you may find in actual data as well. So stay tuned for that, and at the very end I will give you some tips for how you can detect suppression in your own data. So stay until the very end and make sure that you get this information as well. Now that we've seen an example of classical suppression in a data example, I want to talk more formally about how we can define suppression mathematically and how you can detect it. So first of all, let me summarize what we've seen so far in terms of what a suppressor effect is. So a suppressor effect is a phenomenon in either regression or path analysis or related techniques such as structural equation modeling, where the regression coefficients take on an unexpected sign or magnitude in terms of the standardized regression coefficients. We saw that the size of those standardized regression coefficients was surprising. They were above 1, one was above 1, one was below 1, one was negative, even though the zero order correlation was weakly positive. So that was unexpected. And that's maybe the most obvious sign of a suppressor effect. However, regression coefficients with suppression may not always look so clearly like they are abnormal or unusual. So you may not see that always when only looking at those signs. And therefore it is important for us to also talk about other diagnostic tools. How can we identify a suppressor effect in our data? And so for that, it is useful to consider the concept of utility of a predictor variable xj. So x is a predictor variable, and the idea is that the utility of x can be defined as the difference between the r squared, including both predictors, x1 and x2, and the r squared without that predictor. So when we have a reduced model where we remove xj from the equation, then the r squared will be smaller, and so then we can look at the difference, and that is equal to the squared semi-partial correlation of the criterion variable with that predictor, partialing out all remaining predictors, all k predictors from that predictor xj. In this case, it would be only the second predictor. So when we have only two predictors, then it's a semi-partial correlation between y and xj, partialing out the second predictor. And so then that is squared. The squared semi-partial correlation gives you the utility of xj. Now, why is that useful? Because this shows you can compare this xj to another measure, as we will see. In the suppressor situation, according to Velleser, is given when the utility of that predictor xj is greater than the squared zero order correlation of that predictor with the criterion y. So notice that now on the right hand side we have a zero order squared correlation between y and that predictor, whereas on the previous slide we had the squared semi-partial correlation. So when we partial out another predictor, and then that utility, that squared semi-partial correlation, is greater than the squared zero order correlation where we do not partial out a second predictor. Then we have a suppressor situation. So basically it means if this predictor becomes more useful when it is considered in the context of another predictor, then we have suppression. And so that would always be given when uxj is greater than the squared zero-order correlation between that predictor and the criterion. So that's a good diagnostic tool and a good definition of a suppressor situation that is very simple, or pretty simple. It's pretty simple to calculate that difference in R squared, or the difference, or the squared semi-partial correlation to determine uxj. And then you can very easily look at whether uxj is greater than the R squared between that predictor and the criterion variable. Now, classical suppression is what we've already seen in our example that was described by Horst in 1941. And classical suppression is defined by three correlations, so to say. The first correlation is between the suppressor x1 and the criterion y. And so when that correlation is 0 or near 0, that's, so say, the first condition, the first situation or scenario that has to be present for classical suppression. And then second, when the correlation between x1 and x2 is not 0, so when it is substantial and positive, in our case it was 0.8. And then third, when the multiple correlation between the criterion y and the two predictors included in the regression model is greater than the zero-order correlation between the criterion and the second predictor. And remember that that was also the case in our situation, where the correlation between job success and exam score was above 0.5, so that was a substantial correlation. However, the multiple correlation that also included the verbal ability scores was much higher, so that was above 0.8. So that was also here in our situation was the case. So we had a situation of classical suppression in our data example. Now, classical suppression is not the only form of suppression, and that's important to realize because you may encounter one of the other forms of suppression in practice. So what other types of suppression are there? Classical suppression we already discussed, where x1, the suppressor, and y are uncorrelated or nearly uncorrelated, whereas x1 and x2 are substantially correlated. Negative suppression means that x1 and x2 are positively correlated with y, so both of them. However, one of the standardized regression coefficients is negative. And then there's also reciprocal suppression, where x1 and x2 are positively correlated, but they're negatively correlated with y. So a situation like that can also occur. Now, how can you detect suppression in practice? How would you find out whether you have an issue of suppression? And so for that reason, it is, or to detect that, it's always very important, as I already mentioned, that you take a look at your observed correlations. So take a look at the bivariate correlations between all the predictor variables and the criterion variable, because those zero order or bivariate correlations are very important for detecting suppression. And then one clear sign of suppression is when the standardized regression coefficient for a predictor variable, so beta x standardized, or the absolute value, I should say, of beta x standardized, is greater than the absolute value of the bivariate or zero order correlation between that predictor and the criterion variable. In that situation, you can be certain that you have suppression, or you can also use the definition earlier with the utility of the predictor, and you can check on that as well. Now, clear signs of suppression are also when you have unexpected signs of regression coefficients. So unless you have a data error or an analytic problem or something like that, or a missing data problem, if you have an unexpected sign of a regression coefficient, that could very well mean that you have suppression. If you have a standardized regression coefficient that is abnormally large, that is maybe greater than 1 or smaller than -1, that could also point to a suppressor situation. So my tip here is, my recommendation is always check the zero order correlations, compare the zero order correlations to your standardized regression coefficients, and then that way you should easily be able to detect a suppressor effect. Now, is a suppressor effect a bad thing? Does it mean your regression is invalid or that you can't use it? No, absolutely not. A suppressor situation can actually be a good thing, because as we saw, it increases your R squared of your regression model, which means you can better, more precisely predict your dependent variable scores. You can make better predictions. You can explain more variance in the dependent variable, so that can be a good thing. However, one thing that comes with suppression is that the regression coefficients, so the slope coefficients, may be more difficult to interpret, or they may be meaningless because the sign may have shifted in a way that it does not allow you for a very meaningful interpretation of those coefficients. However, the overall R squared is not affected by that. Now, one problem, of course, could be if you have multiple suppressor variables, you have very highly correlated predictor variables, you could run into a problematic scenario of multicollinearity where your standard errors maybe are very high because your predictors are so highly correlated. In that situation, you have to consider whether some of the predictors are redundant and should be removed. But in principle, a suppressor situation is not necessarily a bad thing and not a reason to abandon your regression model. Now, another thing to remember is that suppression does not only occur in regression analysis, it also can happen when you have a path model or a mediation model, or when you have a structural equation model. In structural equation models with latent variables, it is particularly likely because you correct for measurement error, and so you have even higher correlations between your variables, oftentimes because of the correction for attenuation that is built into the measurement model. And so that can happen there as well. It can also happen in multi-level models, which are generalized regression models. It could also happen in a logistic regression model, not just linear regression. So keep that in mind. And so when you find results that you find abnormal or that confuse you, then think of the fact that this might be an indication of a suppressor situation. I hope you found this video useful. To learn more about suppression in statistical analysis, please consider subscribing to this channel. Check out the description for additional resources, and I'll see you next time.